Hey, welcome to the Explainer. Ever wonder how your GPS just knows the fastest way to get somewhere? Or how a social network can recommend someone you might know, a friend of a friend? Well, behind all that magic is this really elegant, super simple idea called breadth first search.
So let's just think about this for a second. Imagine you've got this huge, sprawling network. It could be anything, right? A social network, a map of a city, even the entire internet. How in the world would you go about exploring it, but in a smart way? Like layer by layer, making sure you don't miss anything and don't just get lost wandering down some random rabbit hole.
Well, the answer is this awesome algorithm called breadth first search, or BFS for short. And it's actually super elegant. The best way to picture it? Think about dropping a stone in a pond. You see those ripples spreading out, one circle at a time? That's exactly what BFS does. It explores everything in one layer, then the next layer, then the next. Super methodical.
All right, so before we dive into how BFS pulls off this elegant trick, I think it's really useful to look at what happens when you don't have a smart system. Let's talk about let's call it the brute force idea, which is way more flawed. Okay, so look at this comparison. On one side, you have the brute force method. It's just chaos. You're wandering all over the place, maybe even visiting the same spot over and over again. It's a total mess and super inefficient. But then you look at BFS. It's the complete opposite. It's systematic. It's orderly, going level by level. It's just optimal.
So the big question is, how does BFS actually work? How does it manage to be so efficient and elegant? Let's get into the nuts and bolts of the algorithm itself. Okay, the whole thing really boils down to 3 core steps. And to make those steps happen, it relies on 2 super important tools. You can think of them as a to-do list for keeping track of where we need to go, and a memory to remember all the places we've already been. Simple, right? So that first tool, our to-do list, is called a queue. And the analogy here is perfect. It works exactly like a line at the grocery store. First one in is the first one out. Whatever node gets into the line first is the next one we're going to look at. And this simple first in, first out rule, that is the secret sauce. That's what guarantees we explore level by level. And the second tool, the memory, is usually just a list or an array we call the visited list. And it does exactly what its name says. It's the algorithm's memory bank. It just keeps a record of every single node it's already visited. Why? Because this is what prevents that chaotic mess we saw earlier. We don't do the same work twice. It's all about efficiency. All right, theory is one thing, but seeing it work is way better. So let's actually put this into action. We're going to take a simple little graph and walk through it, step by step, so you can see exactly how the queue and the visited list play together. Okay, here we go. We're going to start our search at node 0. So, first step, we add node 0 to the queue, our to-do list, and we also mark it down in our visited list. Done. And now the real work starts. We take the first thing out of the queue, which is node 0. We ask, okay, who are your neighbors? It's node 1 and node 2. We check our memory. Have we seen them before? Nope. So we add both of them to the back of the queue. And just like that, look at our list. The queue has changed. Node 0 is gone because we've processed it, and now nodes 1 and node 2 are waiting in line. And our visited list, it shows we've now been to nodes 0, 1, and 2. All right, next up, remember first in, first out. So node 1 is at the front of the line. We pull it out, we look at its neighbors, and we find node 3. We haven't been there yet, so you guessed it, we add node 3 to the back of the queue. You can really see the system at work now, can't you? Node 1 is done, it's out of the queue. Node 3 is now waiting at the end of the line. And our visited list keeps track of everything. Okay, who's next in the queue? It's node 2. So we pull it off, check its neighbors, and hey, there's node 4, which we haven't seen. So we mark node 4 as visited and pop it onto the back of the queue. And check this out. Our visited list is now full. We've technically seen every single node in the graph. But, and this is a really important point, the algorithm doesn't stop here. It only stops when its to-do list, the queue, is totally empty. So we keep going. We process node 3. Does it have any new neighbors? Nope. Then we process node 4. Any new neighbors there? Nope again. As we process them, the queue gets shorter and shorter until it's finally empty. And that's when the algorithm knows it's finished. So what's the final order we visited things in? We went 0, then 1 and 2, then 3 and 4. You can literally see the layers. It's a perfect demonstration of that ripple effect we talked about. It's clean, it's orderly, and it's just so efficient. Okay, so we've seen the logic. Now let's peek under the hood a little bit. What does this look like in actual code? And more importantly, how fast and efficient is it really? Let's look at its performance report card. Now, don't worry if you're not a coder, you can totally appreciate how clean this is. This C++ code is basically a direct one-to-one translation of the steps we just did. You can see right there where we create the queue, where we push and pop nodes from it, and that all-important if statement that checks our memory, the visited list, before we do anything. So how fast is it? Well, in a word, fantastic. The technical term is OOV plus E, time complexity, but what that really means is just that it's super, super efficient. All it's saying is that the algorithm is guaranteed to visit every single node, that's the V, and every single connection or edge, that's the E, exactly once. That's it. No repeated work, no wasted time. And memory usage, also really good. The amount of memory it needs is basically tied to the number of nodes in the graph. The worst case scenario is that the queue has to hold all the nodes from the single widest level of the graph, but for most real-world problems, that's totally manageable. So if there's one thing to remember, it's this. Because BFS explores layer by layer, it is the absolute champion at finding the shortest path between 2 points. It's guaranteed. But that leaves us with a really interesting final thought, right? What if you didn't need the shortest path? What if you just wanted to find any path, no matter how long and twisty it was? What if your goal was just to dive as deep as possible to see if a connection even exists? Well, for that kind of problem,